For centuries, humanity has sought to understand the universe, building layer upon layer of knowledge in an attempt to explain the vast cosmic reality that surrounds us. From the early observations of the night sky to the formulation of gravity and the development of modern physics, each discovery has brought us closer to a coherent picture of existence. Over time, this picture evolved into a powerful and elegant narrative. The universe began with the Big Bang, expanded over billions of years, and gradually formed the galaxies, stars, and planets we observe today. For much of the 20th and early 21st centuries, this narrative appeared remarkably successful. It explained the large-scale structure of the universe, the distribution of galaxies, and the faint afterglow of the Big Bang itself. Cosmology, as a field, seemed to have reached a point of maturity, a stage where the fundamental questions had been answered and only finer details remained to be filled in. Yet, science is never truly finished. As our instruments became more precise and our observations more detailed, subtle inconsistencies began to emerge. Measurements that should have agreed started to diverge. Predictions that once seemed reliable no longer aligned perfectly with reality. And, most strikingly, entirely new observations began to reveal phenomena that should not exist according to our current understanding. These anomalies are not isolated curiosities. They are persistent, measurable, and increasingly difficult to ignore. Together, they point toward a profound possibility that the model we rely on to describe the universe, our best, most refined theory of cosmology, may be incomplete. This is the beginning of a scientific crisis, not a collapse of knowledge, but a turning point. A moment when the universe itself appears to be telling us that something fundamental is missing. At the heart of modern cosmology lies a framework known as the Lambda CDM model. This model is widely regarded as the standard description of the universe, combining Einstein's theory of general relativity with observations of cosmic expansion and structure formation. It provides a mathematical and conceptual foundation for understanding how the universe evolved from its earliest moments to its present state. According to this model, the universe is composed of three primary components. Ordinary matter, the atoms that make up stars, planets, and living beings, accounts for only about 5% of the total. The remaining 95% consists of two mysterious substances, dark matter and dark energy. Dark matter, which makes up roughly 27%, is thought to provide the gravitational scaffolding that allows galaxies to form and remain stable. Dark energy, comprising nearly 68%, is believed to drive the accelerated expansion of the universe. The strength of the Lambda CDM model lies in its ability to explain a wide range of observations with remarkable accuracy. It successfully predicts the patterns seen in the cosmic microwave background radiation, the large-scale distribution of galaxies, and the overall expansion history of the universe. These successes have made it one of the most robust scientific models ever developed. However, this success comes with a caveat. The model depends heavily on entities that have never been directly observed. Dark matter has not been detected in laboratory experiments, and dark energy remains entirely theoretical. In essence, we have constructed a detailed description of the universe based on components that we cannot directly see or measure. This does not necessarily invalidate the model, but it does introduce a degree of uncertainty. It means that while the model works, it may not be complete. And as new observations begin to challenge its predictions, that uncertainty becomes increasingly significant. One of the most compelling pieces of evidence that something may be wrong with our cosmological model comes from a problem known as the Hubble tension. This issue arises from attempts to measure the rate at which the universe is expanding, a value known as the Hubble constant. There are two primary methods for determining this expansion rate. The first involves observing the early universe, particularly the cosmic microwave background radiation. By analyzing the patterns in this ancient light, scientists can infer the expansion rate based on conditions shortly after the Big Bang. The second method involves observing nearby galaxies and measuring their distances and velocities directly, using objects such as Cepheid variable stars and Type 1a supernovae as cosmic distance markers. In a consistent and well-understood universe, these two methods should yield the same result. However, they do not. Instead, they produce values that differ significantly, far beyond what can be explained by measurement errors or uncertainties. This discrepancy is deeply troubling. It suggests that either one of the measurement techniques is fundamentally flawed, or that our understanding of the universe's expansion is incomplete. Increasingly, scientists are leaning toward the latter explanation. The Hubble tension is not merely a technical problem. It strikes at the core of cosmology, challenging the assumption that the universe behaves uniformly across time and space. If the expansion rate cannot be consistently measured, then the underlying model that describes that expansion may need to be revised. The launch of the James Webb Space Telescope marked a new era in observational astronomy. Designed to peer deeper into space than any telescope before it, Webb allows us to observe the universe as it existed in its earliest stages. By detecting infrared light from distant galaxies, it effectively acts as a time machine, revealing the conditions of the cosmos just a few 100 million years after the Big Bang. What Webb has discovered, however, has taken scientists by surprise. Instead of finding small, faint, and primitive galaxies, as predicted by current models, it has revealed galaxies that are large, bright, and highly evolved. These galaxies appear to contain vast numbers of stars and exhibit complex structures that should not have had enough time to form. This creates a profound problem. According to the Standard Model, galaxy formation is a gradual process. Small structures form first, merging over time to create larger systems. This process is expected to take billions of years. Yet Webb's observations suggest that massive galaxies were already in place within a fraction of that time. The implication is clear. Either galaxies can form much faster than our models allow, or our understanding of the early universe is incomplete. In either case, the discovery challenges one of the fundamental assumptions of cosmology, that the timeline of cosmic evolution is well understood. Dark matter plays a central role in the current cosmological model. It is invoked to explain a variety of gravitational phenomena that cannot be accounted for by visible matter alone. For example, galaxies rotate at speeds that would cause them to fly apart if only ordinary matter were present. Similarly, clusters of galaxies remain bound together despite having insufficient visible mass. The concept of dark matter provides a convenient solution to these problems. By introducing an invisible form of matter that interacts through gravity but not light, scientists can reconcile these observations with the laws of physics. However, despite decades of effort, dark matter has never been directly detected. Experiments designed to identify dark matter particles have consistently failed to produce conclusive results. This has led some researchers to question whether dark matter exists at all. An alternative possibility is that our understanding of gravity is incomplete. Modified theories of gravity attempt to explain these phenomena without invoking dark matter, suggesting that the laws of physics may behave differently on large scales. If this is true, it would represent a fundamental shift in our understanding of the universe, comparable to the transition from Newtonian mechanics to Einstein's theory of relativity. Even more mysterious than dark matter is dark energy, the force believed to be responsible for the accelerating expansion of the universe. This discovery, made in the late 1990s through observations of distant supernovae, fundamentally changed our understanding of cosmic evolution. Before this discovery, it was assumed that the expansion of the universe would gradually slow down due to the gravitational attraction of matter. Instead, observations revealed that the expansion is accelerating, implying the presence of a repulsive force. Dark energy is the name given to this force, but it remains one of the greatest mysteries in physics. It could be a property of space itself, a new type of field, or something entirely unknown. Recent observations have raised the possibility that dark energy may not be constant, but could change over time. If this is the case, it would have profound implications for the fate of the universe and the validity of our current models. Throughout the history of science, moments of crisis have often led to breakthroughs. When existing theories fail to explain new observations, they are not discarded lightly. Instead, they are examined, refined, and sometimes replaced by deeper and more comprehensive frameworks. Cosmology now stands at such a moment. The Hubble tension, the unexpected discoveries of the James Webb Space Telescope, and the unresolved mysteries of dark matter and dark energy all point toward a universe that is more complex than we imagined. These are not signs of failure, but indications that our understanding is still evolving. Perhaps cosmology is not broken. Perhaps it is simply incomplete, and if that is the case, then we may be on the brink of a new scientific revolution, one that will reshape our understanding of the universe and our place within it.
Thanks for watching Astrotech. If you found this video helpful, don't forget to like, share, and subscribe for more amazing tech content. See you in the next video. Stay curious, stay innovative.